This is the section 5, chapter 5, section 6 presentation on numerical integration. Oh, so let it be known that you've already done numerical integration. When you did the left 4, let's say, and the right 4 um, rectangles to try to find the area under a graph, you are doing numerical integration. And we did midpoint 4, and we did trapezoidal 4, which of course was L4 plus left 4 plus right 4 averaged. So we did those before. They just want to do a little bit more of an improvement on this, and they want you to understand something about how this works. So I am going to do just this brief presentation on this section, looking at this table 5.6.5. And they said, look at this. And so I want you to look at this and see that as y equals 1 minus x squared, and we're trying to find the area under this parabola. So if I were to graph that with some degree of carefulness, it's an upside down parabola moved up 1. So if that's 1 and moved over 1, it would go through 1. So it looks something like that and goes through minus 1. And if we're doing it from 0 to 1, we're finding the area in here. Just this area, right, bounded by that. And I don't want to write on that yet because I'm going to need to do some other markings on that. The other one they're asking us to look at is y equals 1 over x squared. And we're especially interested in from 1 to 2 on this. So 1 over 1 squared is 1, and 1 over 2 squared is 1/4. It looks like something like 1 over x squared, except on this side it does it this way. So they're looking at the area under this curve on this side. And the reason they chose these two is this one, they're both decreasing, and this one's concaved down, and this one's concaved up. And that's kind of what they want you to see here, the important things. So, and this is an easy integration to do, so you could integrate this and evaluate from 0 to 1, and it comes out to be exactly 0.066666, or 2/3. This area right here is 2/3 exactly. We know that. But let's assume that this was some kind of curve that we couldn't do that. But since we do know it, we can compare the different methods that we have for accuracy. Now, you've already seen that left and right are one's going to be an over and one's going to be an underestimate. Midpoint is better, and trapezoid is better than left or right. These are both better than left or right. Now, which one of those is better? And so we're going to look at that a little bit. So if they're saying do trapezoidal 4, we're going to split this into 4 sections. So I'm going to try to get this up here far enough. So that means we're going to have rectangles at 1, and we're going to do up to the curve and over if I'm doing right, and if I'm doing left, it's coming from the curve and down, curve and down, curve and down. One's going to be over and one's under. But trapezoidal, I would do connect the 2 points at the top. And if you look carefully, you can see that if it's curved down and you're doing trapezoidal, it's going to be an underestimate. Now, if I did midpoint, then I would be doing get a different color here. Where's my red? I would go to the midpoint and go up and make a rectangle. So part of it would be over and part would be under. If I go to the midpoint on this one, part would be over, part would be under. And if I go on this one, part would be over and part would be under. If I went on this, just this enlarged, it would be at the midpoint. And the midpoint will turn out to be a little bit over on a concave down curve. On a concave up, the midpoint would be a little bit under, and the trapezoidal will be a little bit over. So, what they did trapezoidal 4. Trapezoidal 4, we think will be an under. This is the value they got by splitting this up and doing the left at 0, quarter, half, and 3/4, right using the quarter, half, 3/4, and 1, the heights of those, and multiplying by the width of a quarter, and averaging those two, they got this number. And notice it's a little bit less than the 2/3. 2/3 is 0.6666. This is the difference. This is how much error there is. That's why they called this the error column. The trapezoid is an underestimate. The midpoint is an overestimate. Then they did it all again doing 8 subdivisions, so we'd have to 8 quarter, 3/8, half, 4/8, 6/8, 7/8, whatever. And they did them again, and again the trapezoid is an underestimate, and the midpoint's an overestimate. They did the same thing over here, trapezoid 4, and the actual area is a half. This area is 1/2. They got this, which was an overestimate. The trapezoid on a concave up curve is an overestimate by this much. The midpoint is an underestimate by that much. Then they did it with 8. We got an overestimate and an underestimate. So they just kind of reverse roles. Now, the whole point of this is, if the trapezoidal is always going to be over and the midpoint is under and the midpoint is going to be over or vice versa, then the true value, which we happen to know in here, but if we had a curve where we didn't know the equation, the true value would be somewhere in between. And if we look closely at these numbers, you'll notice that this is 0.005 and this is 0.010, or 10 thousandths, and this is 5,000. This is about twice as big, only negative. But if you forget the negative, this is half as bad as that one is. And this one's half as bad as that. This one's half as bad as that. And this one's half as bad as that. The midpoint is twice as good an estimate as the trapezoid. But because it's always going to be on below or above, and the other is above or below, if we do an average of 2 of these to 1 of those, we're going to get really close to the answer. And that's what a gentleman called Simpson did. He said, if you take 2 of the midpoint values plus 1 of the trapezoidal values and divide by 3, remember we're going to have 1, 2, we're going to have twice as much as we need here plus another one, so that's 3. Divide by 3, we get an average of 2 of those and 1 of those. He's going to call that a much better estimate of the area under the curve. Now, the reason they do 2n here is because when we were splitting this up, it actually creates 8 points in here, the midpoint ones and the left and right ones, and so we get 8 points in there, so they say, well, that's twice as many. So Simpson 8 is a midpoint 4 plus a trapezoidal 4. A Simpson 16 is a midpoint 8 and a trapezoidal 8. So down here, same equations. How did they compare? So these two lines are exactly what was on the previous table I showed you. And then they did the Simpson 8, which is 2 of those plus that divided by 3. So they took 2 of the midpoint ones plus the trapezoidal one divided by 3, and they got this. And notice this was 0.666 repeated, which is 2/3. There was no error at all on this upside down parabola. In fact, when they went to more deal, do trapezoid 8, midpoint 8, so they take 2 of those plus 1 of those, add them up, divide by 3, and they got this, no error. On the concaved up one, they took 2 of these plus 1 of those, got this number, and that is so much closer to the correct answer than those two. Really close. Off by not hundreds, tenths, 100,000, 10,000s, 200 thousandths off of the 0.5. And if you did it with 8, it even gets closer. Tenths, 100,000, 10,000s, 100,000s, a millionth. Only 2 millionths off of the correct value. So if you were working with numerical data where you only knew points, and you wanted to get a good approximation of the area under this curve, to get their best one, according to Simpson's rule, would be to do the midpoint rule on it and the trapezoidal rule on it, and then take 2 of the midpoint plus the trapezoidal rule, add them up, divide by 3, and you'd get a really good approximation of the area under the curve. That's the main thing that they wanted you to see in this.